Hello, welcome to this evening. To be honest, I don't know what you've been told already because we couldn't hear what Martin was saying. So you probably know this is a celebration of the work of Ernest Rutherford and his life, and it's 150 years since he was born. And with luck, this will be one of the last times that we do events where we're all just in the different kind of locations where we've been for the last year. But it is a pity in one way because I've had some just before we started doing this, there was a cat just outside my window which was going through that springtime thing that cats go through. It's very noisy and it's rather unsettling, and it's just stopped. So if you do hear that at any point, that's just part of the joy of the way that we're having to do all these shows as these kind of things continue. But as I said, hopefully very soon we're going to be back in theatres and places like that. So we've got a great list of people. Again, you might have been told all this. I'll be joined by Helen Czerski. We're going to be joined by Jim Al-Khalili, Linda Cremonesi, John Butterworth, and with luck, by the end of it, we will understand everything that we've never understood before about the nature of the atom and the discoveries of the last 100 years. I would highly recommend after this you watch, there's a lovely little bit of film from I think 1936 of Ernest Rutherford, which you can see on YouTube, just talking, I think as far as I remember, about nuclear fission. But it's a really beautiful thing of just an elderly man sat by a desk having to wait for the camera to come. So like a wobbling camera, you can almost hear the wheels, and he just sits there and just waits and then goes, "Hello, the atom." Anyway, have a look at that. It's an absolute delight. I'll tell you a few things. First of all, I'm sure Martin mentioned it, but please do support the Royal Institution. This has been a very tough last kind of 400 and however many days for so many institutions which have relied on the creation of live shows normally and people actually coming to them. We do Cosmic Shambles. I've been doing a huge number of things with Helen Czerski. I've been doing every Sunday we do a live science Q&A at 3 p.m. So if you get the chance, join us one Sunday. It's at Cosmic Shambles. We've had loads of different guests. Brian Cox and Jim actually has been on, and we also do Tips for Existence series, which recently on Tips for Existence we've had amongst others Carlo Rovelli, who is just one of the most amazing minds. You know, I suffer from mind envy quite a lot, and I don't know how many of you out there have mind envy, and in fact pretty much everyone I'm going to be speaking to tonight, I have mind, because there's a point where they reveal a certain level of knowledge where you just feel so, I just don't know how have they been able to grasp these magnificent ideas, and I realised I just have to work a lot harder. But yes, Carlo Rovelli and Andrian and Tim Minchin and Brian Green, and this week Chris Jackson, Sarah Parkat, many others. That's on the show, Cosmic Shambles show we do called Tips for Existence. Anyway, find all those things at cosmicshambles.com. After this show, well, not after this show, that'd be a terrible time to do it, but near the end of this show we are going to have a Q&A as well. So if you want to send questions in, our producer Trent will make sure that I get those questions. Again, any questions kind of looking at Ernest Rutherford, the knock-on effects of Ernest Rutherford's work, indeed 21st century, as many of you will know, we continue to have a changing understanding of what it is that actually makes an atom and why an atom is the way it is. So any questions on that, we can go up to date as far as 2021 on those questions, and probably about as far as 76, but we'll try to go no further back than that in those questions. And I'm now joined by Helen Czerski. Hello, Helen. How are you?
I'm doing very well. Hello.
When did you first become aware of Ernest Rutherford, like in study? Because many of us who've not gone on to study at college or university, these names are not ones that we ever actually hear in the classroom when we're at school, these pioneers.
So almost the problem with Rutherford, I think, is that so most people do one very big thing and they're famous for that one very big thing. And almost the problem with Rutherford is that he did so many things and they're all amazing, but because there's so many of them, he's not remembered for one thing. And so he sort of isn't remembered for any of them, which is a terrible, terrible shame, but it's just, he did so much, it's almost hard to remember. So I must have been told about Rutherford at school and during A-levels, but the first time I remember thinking about him as a person, as a physicist, was during I studied physics at Cambridge, and on the new museum site there, which is part of the university, there is a building, a sort of sand-coloured building that was right next to one of our major lecture theatres, and it's slightly weirdly got this massive crocodile that is sort of etched into the side of the brick, and it's a bit weird. Like there's all the, there's buildings, it's university, and there's this crocodile, and the reason the crocodile is there is because a guy called Peter Kapitsa, who was a physicist in the Cavernous Laboratory, which is where Ernest Rutherford worked when he was at Cambridge, called Rutherford the crocodile, and he was so impressed by him and his sort of influence on all the physics that he had this crocodile put on the side of the building where the old Cavendish laboratory was. And so I remember asking, what's this crocodile doing here? And really, as an undergraduate at Cambridge, then Rutherford's role sort of kind of keeps unraveling, because he's at the bottom of everything, like everything we teach about how the atom is. If you've got to think about, Rutherford was born in 1871. And so at that period, you're towards the end of the Victorian era. There's a lot of steam engines. There's an industrial revolution. People sort of feel physics is sort of sorted out. After that, it's just the tidying up. And he died in 1937, I think, just before the Second World War and the nuclear bomb. So he covered this whole period of the discovery of X-rays, physics getting really messy, overlapping with people not even really knowing, people weren't absolutely convinced that atoms existed when Rutherford was born. And then he went on to just work out what atoms are, how they work, all these things that are actually very basic chemistry now. And the Nobel Prize he got was in chemistry. And he was just underneath, so that's there at the back. Well, he was at the forefront, but he was, right deep in there into all these physics discoveries. So he got the Nobel Prize quite early in life. I think he was 35, and he won it for discovering radioactive half-life. So all those we think about now of radioactivity dying away over time. Well, he worked out why. He worked out there's a time period where if you wait that time period once, it halves. If you wait that time period again, whatever you've got left halves. And he worked all of that out. But he also, the experiment he's most famous for, he was delving around, what is an atom? What's it doing there? And he did this when he was, so he's a New Zealander. He moved to Cambridge, then went to Canada, came to the University of Manchester, and it was there that he did these experiments with gold foil. And this is what he was really, of all the amazing things he did, this is the one he was famous for. That there was this experiment where there was gold foil, people were firing alpha particles at it, and the picture of the atom at the time was that it was a kind of cloud of stuff. It didn't have any real shape. And he found that if you fired these helium nuclei at it, some of them bounced directly back at you. And it was thought that the atom was this kind of fuzzy, messy, like there wasn't, it wasn't concrete. And then he said, there's this quote that I've got it here. He said that when he, I had it written down because it's such a good quote. But basically he said that it was an astonishing thing that if you, I've lost my quote, that's terrible, that it was like firing an enormous, almost a cannonball at a piece of tissue paper, and it bounced back and hit you. And that was the demonstration that the atom has a nucleus right at the middle, and that's where most of the mass is, and all the electrons are sort of little light things around the outside. So he was right in there, and the discovery of the proton, what radioactivity is. He was head of the Cavendish Laboratory, this big lab in Cambridge, and he was just like there, the proton, the neutron. He worked under J.J. Thomson when the electron was discovered. He was just like there all the way through, and by accounts he was also a very nice man, so that's all good.
It's such an interesting thing. I presume would probably have been a teenager when Lord Kelvin famously said that physics was basically finished now. It was just kind of the decimal point work pretty much was all that was left, and that seems to be it's almost I know this is playing around a little bit with the timeline, but it's reasonably close to there that suddenly everything opens up and we see so many revolutions of our beginnings of our understanding of what makes everything what it is, from the smallest thing to the universe.
And it did come as a shock, but also it was X-rays that sort of started that they were there was something they really couldn't explain. And Rutherford was quoted as saying that he compared it to a race, and he said, I think the Curies and Becquerel were the sprinters in this race, but he painted this picture of all physicists. They knew what the goal was. The goal was to explain this weird thing, and everything was sprinting in that direction. And a lot of the things that I think one of the reasons he's perhaps not known so well is around that time, a lot of the things that were getting a lot of public attention were quantum theory, right? This kind of weirdness, and physics was suddenly going from being clockwork to being thoroughly weird. And the fact that the actual nature of the atom hadn't quite been worked out while all that was going on. That kind of gets lost in all this quantum weirdness stuff. But one of the other interesting things about him is that he was born in New Zealand in a farming to a family that farmed, and he would have grown up in a very practical environment, although it sounds like he was always inventing things along the way. And I've actually been if you drive along that road in New Zealand, it's a tiny village near Nelson, and there's this stone sort of garden that's a monument to him, and it's got this small statue of a small boy, which is supposed to be him when he's a boy. So he came from rural New Zealand, and he was itching to get out. There's a story, I think, that he said when he left, I've collected my last potato, because he was done with digging up potatoes. So he came from this very rural, practical background, and he was an experimentalist throughout his life. He was like, tell me the facts. What's I appreciate your nice theories, but let's build an experiment. And it was he sort of mentored people. He worked with people. And when he was head of the Cavendish, it was said that, people came in late, and at 6 o'clock, somebody was actually tasked with going round and shooing everyone out. Because he said, if you haven't solved your problem by 6 p.m., you need to, go away, have some dinner, think about it, and come back the next day. So he didn't have any truck with this, idea that you should work all the time. He was very human with it, which is a nice thing, and I obviously think contributed to his discoveries. But he was known as the father of nuclear physics. The people have compared his significance to Newton and Faraday, like the big beasts in the understanding of the world, and Rutherford was right up there with them.
What's great about this introduction you've given is it reminds me of back in the 90s when you'd sometimes be backstage at a comedy club, and everyone always gets worried that the first Comic-Con's going to do all the stuff they were going to do. Oh no, I was going to do my bit about getting drunk or American Tourist. And I can imagine, because you've covered so much so quickly, that Jim, John and Linda have gone, well, that's that gone. Well, that's that anecdote out. Because this is what you mentioned, the Cavendish Lab, and let's have Jim join us as well. And I know Jim's going to run us through also kind of a biography and stuff. But the Cavendish, I remember going around the Cavendish Laboratory, and it's just what I love about it when you were talking there about an experimentalist is there are so many different cases dotted around with things that don't have all the clean lines. They have that sense of how can we make this thing which can test this idea, and it has there's some of the things I remember looking at which have a wonderful kind of sense of Meccano and Blue Tack almost about them.
It is brilliant. They were you sort of had to be, right, because there weren't any factories that made this stuff, and it's very important to remember this with the scientists of that time, that they were working with technical experts. They often didn't do the glass blowing themselves, right? They worked with very, very brilliant technicians. And one of the great things about the Cavendish actually is that it's got a photo from every year since, I think it's 1895. And every year there is a picture taken of all the people in the Cavendish, and it goes along the wall. And if you work there, eventually you're on one at the end. But those pictures are it was quite a small group. But yeah, they were very much into getting their hands mucky. But Jim knows far more about. He's the expert on the detail of the history, I'm sure, far more than me.
Jim, can I ask you first of all? Did you, when you were an undergraduate, did you have to do any glass blowing? Because I do know that there are physicists I've spoken to who actually went off and would do glass blowing.
No, I didn't. I think I did have to do some glass blowing from a TV documentary I was filming, but no. I mean, I'm a theoretical physicist. Experiments for me, I got over doing experiments as quickly as I could. But I mean, Helen's right that when it comes to experimental physics, Rutherford, the only person who can hold a candle to him is Michael Faraday himself. I mean, it's nice that we're here part of a RI event. But Rutherford was an enabler as well. He was it wasn't just that he did the experiments, but he could imagine and understand and interpret what others working with him were doing. I remember you talking, Helen, about the all these different instruments and experimental sort of apparatus. I do remember filming one of the first programs I made about 12 years ago now, Atom, and we're filming in the new Cavendish Laboratory. And they have all these different little instruments on display there, but apparently they're not the originals; they're replicas. But the guy who looks after the laboratory said, "No, don't worry. For the film, we can give you the real thing." And it was James Chadwick's neutron gun. So this is a tiny one of the world's first particle accelerator, just for alpha particles hitting a target and spitting out neutrons at the other end. And holding. I remember my director saying to me, "Okay, Jim, I want you to really be excited about this," and I'm shivering with excitement. I'm tears in my eyes, and I'm a theoretical physicist. So some of the things they did were remarkable. But yeah, look, Rutherford's, he's one of these characters. He's larger than life in in every sense. He was a big man. But there are so many stories to tell about him. I mean, the fact that just interesting, Helen, you said he's the father of nuclear physics. Particle physicists, I'm sure John will lay claim to this, will regard him as the father of particle physics. The greatest experimenter of the last century, more than a century now. But he won his Nobel Prize for chemistry, not for physics.
And he was the one that said, it was him that said, all physics or stamp collecting. I think I assume that is correctly attributed to him. So.
I think that's right. That is him. But he also understood, not to be so arrogant as to think that we have all the answers. In fact, that the other story about Lord Kelvin Thompson in the 19th century saying that we've pretty much sorted everything out. Rutherford, there's the story that he got his revenge over Kelvin because at the time there was this debate about the age of the Earth. And Kelvin had said, given how the Earth would have formed and it would have cooled down by now, it can't be any more than 20 to 40. And of course, geologists knew it had to be older than that. So when radioactivity was discovered, and Rutherford understood there's all this radioactive matter inside the rocks, inside the Earth, which is, the radioactivity is producing heat. That meant the Earth could have been warm for much longer, could sustain its heat. So he knew that it was much older than that. He gave this talk. Was it someone would be able to tell me whether it was the RI or the Royal Society?
Well, for this event, it was at the RI.
It was
yes,
the talk
definitely the RI.
Was in the RI, in fact, and Kelvin was sitting in the front row. And Rutherford gave this talk. He had a lump of rock in his pocket that he showed because he understood that by understanding the nature of radioactivity and half-life, he could measure the age of the rock and therefore the age of the Earth, because these radioactive elements would spit out alpha particles. He understood them to be ionized helium atoms. So if he could measure the amount of helium that's captured in these holes within the rock, that could tell him how long these radioactive elements had been decaying and therefore how old the Earth was. So he was going to pull this rock out and show just how old the Earth was. Kelvin falls asleep halfway through his lecture, and therefore he doesn't get to sort of embarrass him. But I think he said he was sort of quite relieved that probably the great Kelvin, quite a fierce character, probably didn't hear him prove his theory wrong about the age of the Earth.
Can I ask both of you really, which is, could there be someone who had this number of areas with expertise now? Have we reached a point where each subject within a subject within a subject requires such a level of specialization that the idea that you could be a pioneer in so many different areas is much harder now? Would that be true or not?
Oh, absolutely. I think it's much harder. I think there's a lot of movement these days towards interdisciplinary research, so working across boundaries, but you are still only bringing in the expertise from your specialist subjects. You don't pretend that you're an expert in another area just because you're talking to scientists from another field. But yeah, I mean, science is so vast now that you couldn't have the likes of Rutherford. Yes, he was a nuclear physicist, but even within nuclear physics, which is a niche area within physics, within the rest of science, you still have now expertise in particular areas, whether you're working on large nuclei or small nuclei, whether you're working on experimental theory, nuclear reactions or nuclear structure. You couldn't even get that sort of breadth across one discipline within physics anymore. So it's I mean, he was remarkable anyway. He was such a genius that he could contribute to lots of different fields. Even at his time, there weren't many people around who could have made such a big contribution in so many areas.
Well, when do you think that? I was going to say, it changes how we told the story of science, I think, because there were times when one person could do many things in many different topics, and those are easy stories to tell. this person discovered this, and it's an easy story, and so we remember it. And I think we're still learning how to tell the stories of science in a way that reflect these collaborative teams, because it's not easy. It's not one person discovered a thing, and so we're in danger of kind of mythologizing things now that don't happen. But Rutherford really was. And one of the interesting things I think about Rutherford actually is that because he got his Nobel Prize really early on, one of the reasons he was kind of noticed is that as soon as he came back to the UK, basically to Manchester and then back to Cambridge, he already had a Nobel Prize, right? He had already made this amazing contribution, and so he walked into the room almost as the big beast. And so that he carried that presence with him, I think, instead of everyone waiting, only recognizing it at the end. Like he was in there right from the start.
And yet he oversaw the famous Geiger-Marsden leaf experiment that discovered what the atom looks like on the inside. He was the one who figured out what it meant. He even though we know, history tells us James Chadwick discovered the neutron, the other particle that makes up the nuclei of atoms along with the proton, and that was in the early 1930s. But Rutherford had predicted the neutron exists back in 1920. He oversaw the very first nuclear reaction. He was the person who really started the way we do science now, government funded public research. The research councils that fund university research here, that come basically taxpayers' money comes from the government. That was something that Rutherford was instrumental in getting up and going. Before that, research was funded by private benefactors or industry or within universities. So he left his mark everywhere within the scientific endeavor within universities. He also enabled so many others. The list of Nobel Prize winners that came out of the Cavendish Laboratory is quite incredible. And you can bet your life they probably owe their start in science to encouragement from Rutherford.
But I think he also, I don't know what you think about this, Jim. It's always struck me that he also, one of the other things is that he was an outsider, right? This Kiwi, upstart little Kiwi, turns up with this fellowship, age 24, rocks up at the Cavendish, and all these people in tweed suits are like, who the hell are you? And though it had been quite elitist precisely because of that. And one of the benefits he had almost, that he came in as an outsider, and he stood up for other outsiders, I guess. Is that a fair representation?
Certainly, in terms of getting funding for young researchers to try and keep them on at the Cavendish, who was the young Irish physicist?
Cockcroft.
Walton.
Ernest Walton, yeah.
Ernest Walton, I think, had run out of money, had run out of funding, and it was Rutherford who ensured that he and others like him got their funding. So, even after he ceased to be so research active himself, he was ensuring that the next generation of physicists will work. So, yeah, he did more than just the discoveries himself, or, some of the great names in science. You think of Einstein, or the only other person probably on par with Rutherford in that sense, enabling others to do research, was probably Niels Bohr. In helping others develop their work. In fact, Niels Bohr himself was also inspired by Rutherford. He came to the Cavendish to work with J.J. Thomson, but it didn't get on with him. And then Rutherford lured him up to Manchester to work with him to try and come up with a mathematical model to describe this new atom, or the structure of the atom that Rutherford was discovering. So even the great Niels Bohr, my all-time hero in physics, probably owes a lot of what he did to Rutherford helping him out.
Can I ask, just to give the audience a sense of the changing understanding of what an atom is? Helen mentioned at the beginning, that kind of that within physics we see this kind of a sense of a general fuzziness, and this was now adding some element of solidity. So say 20 years before Rutherford, what would the perception of the atom have been, and how much, at what point do we start seeing it being broken down from being this, this singular thing?
Well, I mean, but at the end of the 19th century, beginning of the 20th, even the broad consensus that atoms were real. There were still those physicists, chemists, philosophers who argued that matter would be infinitely divisible, that it was continuous. It wasn't made of fundamental building blocks. I mean, we learn now that there were ancient Greeks like Democritus who believed that the atoms, that there were these fundamental building blocks of matter, but that wasn't cut and dry by the turn of the 20th century. Once it was understood that there were these fundamental lumps of matter that we call atom, the prevailing model of the atom before Rutherford, before this famous experiment with the gold leaf firing alpha particles at them, was that the atom, well, we knew it contained electrons because electrons had been discovered at the end of the 19th century, in the 1890s. So we knew there were these elementary particles of electrons, and we knew they had to be constituents of atoms. But electrons have negative charge, and so the atom has to have extra positive charge to cancel it out because atoms are neutral. But it was assumed that those electrons were embedded within a blob of matter that was the atom, and it was known as the plum pudding model. The electrons were the plums within the pudding. The density of this lump of matter was constant throughout its volume, and it was only when Rutherford understood what the Geiger-Marsden experiment meant, and it took him 2 years to figure out what it actually meant, from getting the results to actually thinking, well, this must be the case. It was only then that he realized that most of the atom is in fact empty space. It's just electrons buzzing around in empty space, with a tiny dense nucleus in the middle which carries all the mass, and of course all the positive charge cancelling out the negative charge of the electrons. So yeah, it was his picture of the atom that we still have at school today. Of course, in modern physics, we don't think of the atom like a miniature solar system, with the nucleus like the sun and the electrons like the planets orbiting around it. It's much fuzzier and weirder than that because it's subject to the laws of quantum mechanics. But we still have that picture of a circle and then sort of these other orbits around it. That's the iconic image of an atom. That's what Rutherford first imagined in 1911.
Can I ask both of you, just because I'm always fascinated as very much a non-scientist. This is how often science is coming up with metaphors and similes very often in terms of as we try and understand what something is. Is there something in pop culture? Is there another way that we could see the atom illustrated that you think would make, for those non-scientists who would still be interested in knowing more, that might be a better way of us understanding what an atom is than the models that we normally see, or certainly I did in the classroom?
Well, I'm not sure. One of the brilliant things about physics models is that they're just representations of reality, but it means lots of them can be true if you take truth as a sort of slightly, if you agree on that's what it means. Because I think one of the most interesting things about a lot of areas of science actually is that it's almost like an optical illusion. You see it one way and then you look at the same thing and you see it differently, and they're both true and they both show you different things, but neither one of them are wrong. And so I think these different models, that's the way to think of them. It's like one of those optical illusions where your brain can suddenly see it one way, like you see the face one way around and you can imagine things around that, or you blink and then you see it the other way around, and it's not one or the other. It's genuinely both. But sometimes it's helpful to think of it one way, and sometimes it's helpful to think of it the other way. So I think you're right that there is a sort of fuzzier, there are lots of fuzzy things about atoms that we could do with, but it's not to replace the nuclear model of the atom. It's to be a sort of optical illusion switch for when it's useful. And I think that idea in itself would be useful to teach, because that's what models are. It's this way, this framework or that framework, and they are both equally valid in different situations.
Brilliant. Thank you.
Yeah.
Now, Jim, you're going to join us for the Q&A a little bit later on, aren't
Absolutely.
you?
Yeah, I'll be there.
Brilliant. Thank you so much, Jim. And we're going to be joined by John Butterworth now. And this is I was talking of the radiation as well. There was if anyone lives in Belfast or is when you're able to actually visit Belfast, the Museum of Ulster has this fantastic, in one of the glass cases, it has toys from the 1940s and 50s, and it has this box that was called Fun with Radioactivity, and it actually says contains real uranium. And I just love the fact it was like 1951 this game came out, and it's one of just fun. It feels like something you would have seen in a Ren and Stimpy cartoon. It's magnificent. John, hello, good evening.
Hello, hi.
Now, where should we start with Ernest Rutherford with you then? For you, what is, we were talking a little bit about the starting off really, I suppose, on the tour of the atom, as someone who's obviously, you worked at the Large Hadron Collider, and you've done these incredible, sometimes when I've seen you lecture, these incredible measurements and these incredible, the images that you have been analyzing of us, understanding why there is mass and understanding these things that exist for such a very, very short amount of time, but the necessity of their existence. So take us on a little tour of the atom.
Sure. I think Rutherford is the person, he was the first tour guide on that tour, right? This is where it goes. So you mentioned the Large Hadron Collider, which is great because I don't have to then introduce it. But that's my experiment at CERN, which I'm mentioning it. I'm going to come back to it at the end because in a very definite way, it's the current cutting edge of a journey that Rutherford began. But also because it's 27 kilometers round, which is the circle line roughly in diameter. And if you imagine that being the radius of an atom, the circle line, so zone 1 of London being the radius of an atom, the nucleus, which Rutherford saw for the first time, is the size of a table tennis ball, more or less. Okay, so 100,000 times smaller. And so the key to what Rutherford did really is about resolution. And maybe if you remember one thing from the tour, from the tour of the atom, it should be the relationship between energy and resolution. So what Rutherford was doing was firing alpha particles at gold foil, as you just heard from Jim and Helen, and they had an energy, really quite a high energy for the time, of 5 MeV, which is 5 mega electron volts. That's 1 electron volt is the energy a particle gets if you accelerate it through 1 volt. So a 12-volt battery will get you 12 electron volts. So Rutherford, without any accelerator, just from a decaying radon nucleus, had 5 million electron volts, and that's quite a whack of energy. And that's why he could resolve the nucleus, because as in the model language Helen was just talking about, in fact, we think of waves and particles as being complementary pictures of what's going on in quantum mechanics, in the subatomic world of physics. And so with every particle, there's an associated wavelength. And the higher the energy of the particle, the shorter the wavelength. And if you want to see really small stuff, you need really short wavelengths. And that means you need really high energies. And that already tells you the link between what Rutherford was doing to see the nucleus and what we're doing at CERN with the highest energy beams we can get to try and look even as far as we can into the heart of matter. So the reason Rutherford was able to resolve the nucleus was because these alpha particles had enough energy to do that. And that then you mentioned also, I think, Cockcroft and Walton earlier in the earlier bit of the discussion. And they, of course, this is a very natural progression. They developed some of the first real accelerators where you didn't just have to rely on nature giving you a high energy alpha particle that you could use to hit gold with. You could actually start taking the particles and accelerating them with electric fields and steering them with magnetic fields and then firing them at things. And then the Lawrence Berkeley Laboratory in the US and things took over eventually, and the whole plethora of understanding probing the nucleus first of all and seeing the proton and the neutron, but then also seeing that there's more than that inside the nucleus, and we could go inside the nucleus if you like, but that's kind of the tour of the atom, I would say.
Can I just, because it's been mentioned a couple of times, the famous experiment with the alpha particles and the gold leaf, but I suppose again for people, non-scientists, what actually were the expectations and what actually is, let's try and visualize what is happening and what that vision, as Helen described, how Ernest Rutherford said, the equivalent of a cannonball hitting a piece of tissue paper and bouncing back.
Yeah, exactly. So if you do some basic calculations, which Rutherford and Geiger and Marsden would have done, which say, okay, we know these alpha particles, they've got 5 million electron volts. That's your cannonball. Okay, that's quite a chunky thing on an atomic scale. It's actually a helium nucleus, in fact, coming in with a lot of kinetic energy. Okay, so that's the cannonball. And then you look at, if you can make a gold foil, they use gold just because you can make it very thin and very malleable, right? So they made it really thin as they can, and you say, so how much mass is in this gold foil averaged over a certain area? It's not very much, actually, compared to the amount of energy coming in. It really is like a piece of tissue paper in that sense, okay? So that's the cannonball and tissue paper thing. And what they discovered, of course, is that the averaging the mass over the area of the gold foil isn't the right thing to do, because it's not spread out evenly. It's in little nuggets, and when you hit one of them little nuggets, your cannonball bounces back again. Whereas if it really had been averaged out,
the diagram, John.
Yeah, exactly. If it had been the plum pudding model, which Helen's showing you there, that's that.
You have to explain which one's which. Can you see it?
The one on my right, the one with only the little X's, is the plum pudding model, I think, and the little X's are probably electrons, and the scribbly bit is the rest of the positive charge averaged out over the plum pudding. And that would what it'd be like if it was averaged. Then your cannonball would just punch straight through that. But it's like the one on the left, where the little blob in the middle is where actually most of the mass, overwhelmingly most of the mass of the atom actually is. And so most of the time, your cannonball will just go straight through, because it will mostly, the electrons are too light to perturb it much. It will just punch through as though it's empty space. But every now and then you'll hit the blob in the middle, and then it'll bounce back at you. Thank you, Helen.
I heard I suddenly heard squeaking, and I thought that she's got the felt tips out. I knew that's what that sound was. That was what I'd also just asked now, which is what are we discovering? Well, not merely in CERN, in terms of changing possible understandings of the atom, which many people have been reading about over the last kind of 5 or 6 weeks.
Yeah. So, I mean, it is at some level about the direct waves going up in energy and looking, and that's kind of what we've been doing at my experiment. But it comes back, it's another way of laughing at Kelvin, to be honest, because he said, physics, it's all in the decimal points. Well, the latest excitement in physics has actually been somewhere in the 15th decimal point or something. And in fact, the measurements that established quantum electrodynamics as the theory, Feynman and Schwinger and Tomonaga's theory of the way that the whole standard model is now based on, was from measuring the decimal points, actually, because the quantum loop corrections actually enter in the decimal points. And this is once you get into quantum mechanics and this idea of virtual particles, then measuring something is not just telling you about the thing itself, it's telling you about all the things it can interact with as well. And if on that list of things it can interact with, they're all going around these little virtual ephemeral loops of particles that aren't really real but do have a real physical influence. So they're not real in the sense you can't collect them in a jar. They don't have the right mass, but they have an observable effect on what's going on. And the thing is, if you measure something precisely enough, you could even see the effect of loops of particles that we don't know about yet. And that's what's been going on, this measurement. Two interesting things recently, actually. One was a measurement of the magnetic moment of the muon coming from Fermilab in the United States. And the other was a measurement of some really rare decays, actually at the Large Hadron Collider, but not my experiment, in an experiment called LHCb. And both of those are sensitive to these ephemeral quantum loops, and neither of them are agreeing very well with the standard model, which, remember, the standard model will say, here's the list of loops you have to calculate to get this right. And if you calculate them all, you'll get the right answer. And both of them deviate somewhat. And one of the reasons they may deviate, could be we've done something wrong, it could be the theorists have done something wrong. But the most exciting possibility is that there's other things going around them loops that we don't know about yet.
You just reminded me, actually, you were talking about jars there. This is a slight detail, but I think it's fun, so I'm going to say it. But you were talking about the jars, and I remember around the time that the Higgs boson was discovered, and Peter Higgs was at the Cheltenham Science Festival, and one of the most entertaining things, most satisfying things I've ever seen, I think. So someone had come up with this statistic that there was you'll correct me, John, but there's approximately one Higgs boson in a space the size of a fist. I'm not sure that's quite right, but something like that. Someone had a stat like that, and Dara O'Brien got a jam jar, an empty jam jar, and he got this label, and he wrote on it, "This jar contains one Higgs boson, signed by," and he got Peter Higgs to sign it. Brilliant. And then he put the label on the outside of the jar, and he went around with his jar to everyone. I thought that was great. Anyway,
no, that's cool. But of course, it's not a real Higgs boson. The real one would decay immediately. But yeah, on average, he's probably averaging over all those loops inside the jar, and on average, there's one Higgs boson in there. Yeah, cool. I didn't know that. That's good.
much better. I had dinner with Peter Higgs once, and I'm always tremendously embarrassed and he's quite a shy and quiet man, isn't he? He's a very, very sweet man. And I remember, when sometimes you can hear what you're saying in a second portion of your head going, what's going on? But in a moment of silence, I started to explain to him how if he was ever attacked by a crocodile, apparently there's a certain note you could, that if played on the cello, will stop it in its tracks. And we ended up talking quite lengthily about when you would have a cello with you while being attacked by a crocodile.
Yeah,
so that's why I'm not often invited to dinner with physicists anymore.
Yeah.
Well, if you get to link back to Rutherford, perhaps that was the way they dealt with him as the crocodile, is play the cello near him, and he won't come and get you when you're working too late at night.
I do wonder where the nickname crocodile came from, actually, because he sounds like he was a really friendly chap, and I've never really associated that with crocodiles, to be honest.
So it seems there are two stories doing the rounds. One of them is because Kapitsa was said to be a little bit afraid and was afraid Rutherford would bite his head off. But I think possibly the more realistic one is that because he had a big booming voice, as Jim said, he was a big bloke, you'd hear him coming, and so there was this warning, like the ticking clock in Peter Pan, that you'd know the crocodile was coming. Right. But no, I don't think anyone really knows. But it's now the symbol of the Cavendish laboratory, right? I mean, it's kind of Rutherford and the Cavendish kind of became so intertwined.
Yeah.
For those,
which I have to say, you probably sympathise with me. You have to say, is a shame for Manchester, really, because he did all the really good stuff in Manchester, to be honest. But there you go.
Not that you're biased at all.
I love that way that it's like with Nick going, he was only there a few months. He was over in Dublin a lot. No. All the best bits were definitely there. I actually heard he was nicknamed Crocodile because he was once walking past the Albert Hall and they started playing Elgar's cello concerto and he was unable to move for an entire 9 minutes. So I think that's the story I know.
That's sorted out then.
John, you're going to join us for the Q&A as well, aren't you?
Sure.
I hope. And so to remind everyone, if you have questions, again, as we were talking about the standard model in terms of the work of Ernest Rutherford, I think it's very interesting to John and Helen, that I'm still intrigued by at what point in science, in physics, well, actually, let's just say, did it become impossible to be someone like Ernest Rutherford, a kind of polymath within? When do you think there is a point of knowledge where you just go, this now is this area of specialization? As you said, there is this kind of intertwining, but at the same time, what were the discoveries?
Physics might have been one of the last bastions of that kind of thing, actually, compared with all the, because other things have been studied, like they specialized, like biology. There's a lot of biology. So for example, Alexander von Humboldt was considered to be the last polymath in the natural sciences. So sometime in the 1800s, I think. I'll have to look that up. Someone's going to correct me on Twitter now. But I think in physics, because the discipline of physics is already a little bit of all of science. It was possible later to be a specialist in just that bit.
Yeah, I would say a lot of physicists actually make the mistake of thinking they can do everything, which is not a bad idea sometimes and can lead to disasters other times. I think there's a problem with physics becoming a little too... It's when the perceived leadership of physics actually moved to the theory, and Rutherford may have been the last great experimentalist in that sense. And after, you talk about Dirac and Feynman and Einstein, they're all theorists. Rutherford was an experimentalist who understood why he was doing the experiments, could do the theory at the level that he needed to. And I don't know whether that's impossible anymore, but it's certainly a lot harder. And I think the point at which physics became theorists and experimentalists too firmly was bad. Physics, actually.
It's also the case. So Rutherford was famously in favour of simplicity, and I think he also said if your experiment needs a statistician, you need a better experiment. So I think that the messy world of the mesoscale, the sort of complexity stuff that I was in the natural world, like he wouldn't have approved of that. That was what made him brilliant at that time, that the world needed exactly the type of experiment that he was good at.
Design a better experiment. But of course, if you're an epidemiologist or an astrophysicist, you don't have the luxury of designing your own experiments all the time. But so you do need statisticians. But yeah, Rutherford was par excellence, could create a system that you could understand and would tell you the answers to the questions you were asking, and that's a real amazing skill, which people do still have these days. But it was the fact that he was perceived to be a leader in physics, not just a guy who did experiments. And I do think there's a bit of an issue in the split between theory and experiment these days.
Brilliant. Thank you very much, John. We'll see you again in a minutes, I think. So, as I said, if you want to send in questions, we've got a good 20 minutes at the end to cover any topics you bring up. I should also say now, at this point, we were going to have a wonderful poet, Sunayana, who is from the Octavia Collective, who are amazing. And if any of you might have seen our some of the live shows that we've done at Cosmic Shambles, including the 24-hour Christmas show that we did, and managed to do, we ended up having a scientist from each one of the 7 continents over that period of time. And if it's still online in various different bits and pieces of it with Robert Smith and Tim Minchin and Helen, who started and ended the show, or didn't quite start the show, but you'll find out about that if you go online and have a look at that.
You'll never let me live that down. It's
no, I don't mind it. I think it's perfect. I think that's the great thing, because everything that we always try and do with Cosmic Shambles has some kind of experimental, edge to it, and therefore it's very important that at times it goes wrong. Otherwise, we wouldn't be experimenting enough.
My bike tyres were happy to oblige.
So that was so you can find out more about that as well. And I will also mention, by the way, if you are able to support us via Patreon, patreon.com/Cosmic Shambles, there are, I don't know how many hundreds and hundreds of hours of stuff. Well, in fact, even in the last year, I think we made it's something like 380 hours of programs, so more than an hour a day. And we've done a lot of we did a lot of panels on COVID, as well as the Sunday Science Q&As and all of the other science shows that we've done, and they're all still online, so you can catch up with lots of things there. And it's fascinating. In fact, I watched the COVID panel we did 1 year and 1 month ago, and the predictions and the hopes of where we might be compared to actually where we are in terms of the science, the research, and the evidence-based thinking is something to watch again with a great sense of optimism. So anyway, if you can support us, that's fantastic. If you can support the Royal Institution, that is fantastic as well. And now we're going to be joined by someone who, again, I think, she was on the 24-hour show, and we've done many conversations with her before. We're going to now... Oh, yeah, I forgot to tell you that Octavia, because I went on a tangent there. And what I meant to say about the Octavia Poetry Collective, who you can see on a 24-hour show, is that unfortunately, Sunayana can't be here tonight, but what she is going to do is she's now going to record the poem that she was going to do live, and that will be up when there's going to be a recording of this. And one of the things I'll do with the recording is cut down all of the questions and tangents that I go on and make it appear that I have some level of sanity. That's why we put those things out, but that's going to be up on the RI site and the Cosmic Shambles site as well, and we'll get Sunayana to record her poem. The Octavia Collective are fantastic. Go and seek them out. Very, very beautiful poems about so many different things. But now we are joined to talk about, well, it's time to talk about neutrons and neutrinos with Linda Cremonesi. Hello, Linda. How are you?
Hi, Robin. Hi, Helen. I'm good. Thank you. Thank you for inviting me. It's really good to see you, and it's really good to come on and talk about neutrons and neutrinos. I have to say, Rutherford would have not liked a neutrino experiment, because we do need statisticians. It's a very different game than the Large Hadron Collider. So, we're still part of particle physics, but we're on the low statistics side of things. So our big discoveries are often with like a handful of events.
Well, neutrinos. So this is one of the things, and very often, the empty space of atoms is something that people love talking about in lectures because it kind of grasps people and they get excited about it. And neutrinos are an idea that when people hear about how many neutrinos are passing through them at any moment, it seems, we always imagine that once something has a name, it's going to kind of bump into you in some way. And, the idea that there's something that is actually able to pass through. Can you tell us then what is, for those who don't know, what is a neutrino?
Right, so neutrinos are elementary particles, so they're part of the building blocks of matter and the universe and everything. And just like the word sort of suggests, the neutrinos are neutral, and they're like these really, really tiny particles. And they're produced in radioactive decay, and an example is in the nuclear fusion that is happening in the core of the sun. We have a load of neutrinos produced basically every second, and then these neutrinos come with the photons to Earth. And one of the most striking facts about neutrinos is how abundant they are. So out of like all of these neutrinos that are produced by the sun, we have trillions, literally trillions of them going through our body every second. I think when I do these events live, I like to ask my audience to stick their thumb out and just have a look and just think that every second there is 1 billion neutrinos going through your thumb. So just like 1 billion, and everyone 1 billion again. So when you think of your whole body, that's like trillions and coming continuously. And those are just the neutrinos produced by the sun. We have more neutrinos produced by our accelerators. Avocados produce a certain number of neutrinos if you got avocados in your kitchen. And the second sort of striking fact about neutrinos is that they're, because they're electrically neutral and we have such a tiny small mass, we very rarely interact. So if you make the calculation of, using the interaction probability of neutrinos, we've got trillions of neutrinos going through your body every second, but over a lifetime, you will probably interact with just one of them. So only just one of them will actually really hit you. Most of them, the vast majority, all the others, will just travel through your body as if it was nothing. And I think that's one of the most amazing things about neutrinos. How they're just, everything for them is almost empty space. We just traverse everything, and they travel these extremely long distances as well, so they can be used for neutrino astronomy, and we can use them to look at the most remote corners of the universe.
Well, there's a really interesting thing there, isn't it? Because I think my favourite way of thinking about neutrinos is that they're the second way of the three ways of knowing the rest of the universe is there. Because we can see. So if we were living on Earth and there was no light, then we wouldn't be able to see the sun. But you could get neutrinos. You know the rest of the universe is there because of the neutrinos, like you say, interacting readily. And then when gravitational waves were discovered, that was only the third way. The third line of evidence that the rest of the universe actually exists. And it's a bit weird, isn't it? Why? Tell us. So these neutrinos that don't. So I've been in neutrino detectors, and I've always feel that, that's where the people who buy lottery tickets go, because they're hoping for rare events.
Yeah.
How hard are they in practice? Are we very good at discovering them now?
Yeah, we got pretty good at them. So there's two ways you can study neutrinos. You can either study the neutrinos that come naturally to us, and these are, for example, neutrinos coming from the sun, neutrinos coming from the cosmos. Like we have the neutrinos produced by cosmic ray interactions with the atmosphere, and you can study neutrinos coming from the Earth. These are called geoneutrinos. But you can also make your own neutrinos, and so if you make your own neutrinos, you know what you're making, and it's a lot easier to study. So one of the experiments I work on is called NOVA, and it's based in the US. And what we do neutrinos at Fermilab, and Fermilab is a laboratory where we have a big particle accelerator, and what we do is produce neutrinos. But you're probably asking, how do you produce neutrinos? It's easy. It's very easy to produce neutrinos. You take some protons and actually take a step back. Hydrogen, throw away the electrons. You've got your protons. You accelerate your protons, and then you throw them on a graphite target. So graphite is the same material that is in your pencils. And you need to actually imagine our target is long and thin. And okay, I made this, but it's really like 2 meters long. So it's 2 meters long and quite thin. It's just a few centimeters. So you smash your graphite with protons, and then you get some other particles that are produced, pions, and they're called pions and kaons, and then they naturally decay into neutrinos. And so we produce these neutrinos and then throw them from Illinois, basically just outside Chicago, to Minnesota. That's 800 kilometers. And then we measure we measure the neutrinos we produce and then the neutrinos they get to Minnesota, and see how neutrinos behave. And it's interesting that John earlier mentioned how in the past few weeks we had some hints that the standard model is not complete, the standard model of particle physics, because the first hint that there was physics beyond the standard model was actually in neutrinos, because according to the standard model, neutrinos come in free flavor, and they're called flavor like your Neapolitan ice cream, and I really do want you to picture the three flavors. According to the standard model, they sort of like, they all have the same mass. And so once you produce a neutrino in one flavor, that's it. It stays in that flavor. It's not going to change. Whereas we've verified it experimentally, and a Nobel Prize was actually in physics the 2015 Nobel Prize in physics was given to neutrino oscillations, which was the discovery that neutrinos can change between flavors, and this was the first sort of evidence of beyond standard model, that our standard model wasn't, it's not complete, or it's not everything.
So the question, oh, sorry, Helen.
Yeah. Well, I was just going to, very quickly then, perhaps this one, I was just going to ask whether, do you study neutrinos now to find out more about neutrinos, or is there another question that you can answer if you know about the neutrinos?
So my research is divided in two halves, and I'm one of the people that I'm probably just slightly across two fields. So I'm a neutrino physicist, but part of some of the experiments I work on are to study the properties of neutrinos, and others are to use neutrinos to study the universe. But in some ways, we're sort of coming towards, they're both to actually understand the universe better. One of what I think would be like a Nobel Prize worthy, at least, the discovery in neutrino, if we got it in the next few years, is understanding how they change with flavors and whether neutrinos and antineutrinos behave the same. So if you've never heard of antineutrinos, you need to think of the neutrino's evil twin. You know, you've got Spider-Man and Spider-Man's evil twin. You've got neutrino's evil twin, and these are antineutrinos. And so the antimatter particle corresponding to neutrinos. And when you've got matter and antimatter that they meet, they annihilate. So neutrino and antineutrinos, meeting, they wouldn't really get along. But what we're measuring, and with this experiment, NOVA and Dune, that is an experiment currently under construction, which will be just like NOVA, only like bigger and better. We've got better at measuring these neutrinos. But what we do is we produce the neutrinos in Illinois, then throw them, in this case, from NOVA to Minnesota, and see how they change in flavors. But then we repeat the same experiment with antineutrinos. So as easily as we produce neutrinos, we can produce antineutrinos. And then we check how they change in flavor. And you're probably wondering, why do you do that? Is that even interesting? It's super interesting. It's because it can help explain the matter-antimatter asymmetry in the universe. So Helen earlier mentioned, like, when neutrinos can be one of the proofs as to why we're, there is an outside of Earth with this in a universe around us. But when we look at the universe all around us, we see a universe that is dominated by matter. Everywhere we look, there's matter, and 99 I don't remember how many % of the universe is matter. So a big question is, where did all the antimatter go? Because our theories of the Big Bang, we have as a result an equal amount of matter and antimatter. Whereas when we fast forward to today, so go fast forward from the Big Bang 13.8 billion years, we have a universe dominated by matter. And these differences in antineutrinos and neutrinos oscillation is what might be the key to that, and sort of like understanding why the universe turned out dominated by matter.
Brilliant.